Hi, and welcome to our discussion on atmospheric dynamics. This is our last topic in atmospheric dynamics. In this video, we're going to cover the thermodynamic equation. And you probably remember the thermodynamic equation from previous videos. It was the first law of thermo said dq is equal to c sub v dt plus p d alpha. What that means is that diabatic heating will do one of two things. So heat that is either released by condensation or heat that's absorbed by radiation or by conduction from the ground can either change the temperature of a parcel of air, what we call the internal energy, or it can do work. And that alpha, remember, is related to volume. So that means that it can expand or it can contract. So we're going to take the first law in another form, which has c sub p in it instead of c sub v, and it changes the p d alpha to alpha dp, and we're going to use that to derive the thermodynamic equation. So the first thing that we're going to do with the first law of thermo is divide it by time, or in other words, take the time derivative. So when we do that, we have dq over dt, we have dt over dt, and then our third term is dp over dt. And we start to see some things, or know some things. We know that dp dt, the change in pressure with time, is vertical velocity. Remember that from our vorticity equation and other discussions, also mass continuity. So in other words, as you go up through the atmosphere in time, pressure decreases. And remember that omega is negative for rising motions and positive for sinking motions. So we're going to stick that in for dp dt. So instead of alpha dp dt, now we have alpha times omega. And it looks a little bit more simple. Next, we're going to divide by c sub p. So every term in this equation will be divided by c sub p. And then rearranging this equation algebraically for temperature gives us dt dt, a big T and a little t on one side, and on the other side you've got a term with omega in it and a term with dq in it. So what this means, what does it all mean? On the left-hand side, you've got dt dt, so that's a change in temperature. And then you've got a term that has omega in it, and that's vertical motion. And then you've got a term with Q in it, which is diabatic heating. So we're going to look at these terms in a little bit more detail. First, the dt is a change in temperature. Now, this dt is a change in temperature following the parcel. So remember, that's a Lagrangian reference frame. So as you go up through the atmosphere, go horizontally, temperature's changing with time, and that is following a parcel of air. Now the other terms, we had one that had omega in it, and what this says is as the air rises, remember omega is negative, and as air rises through the atmosphere, omega is negative. That is adiabatic expansion. As air rises, it expands and the temperature decreases. So if omega is negative, that means you're going to have a drop in temperature. That makes sense. Conversely, if air sinks, then omega is positive, and the other side of the equation, the change in temperature following the parcel, is positive. And the last term is diabatic heating. And this is any release or absorption of latent heat. So as air rises, it cools, and you will have condensation. Condensation releases latent heat, so that change in temperature is positive. On the other hand, if there is precipitation falling and evaporation in that parcel of air, that means that energy has been taken away and the change in temperature is negative. So that can also, diabatic heating or cooling also can result from radiation or also from conduction. So what we're going to do now is get this, or make this a little bit messier. And what I mean by that is, on the right hand side we have a change in temperature with time in our equation. And if you remember, that is a Lagrangian reference frame, meaning following the parcel. And we can break that down. We can say that the Lagrangian reference frame, the total change in parcel temperature following the parcel, is a result of local changes in the parcel temperature plus the advective. And we've done this many times before. We did this in our vorticity equation, if you remember. So the total change in parcel depends upon the local change plus the advective, or moving along with the parcel. Notice that the last term of this equation is omega. That's the vertical. So if you move in the x, y directions, temperature changes, but also as you move up and down, temperature changes, and that's what that omega term there is. So going up or down, you'll have a change in temperature as a result of the vertical temperature gradient. So here's our equation for the total change in parcel temperature. We're just going to rewrite it and simplify it. We're going to say that the total change in parcel temperature, in other words, following the parcel, the change in temperature with time, is equal to the local change in temperature with time, plus the temperature that changes as a result of the movement of the parcel, the horizontal temperature advection, and then also the vertical, as the parcel moves vertically, temperature changes also. So that's your vertical temperature advection. So we're going to take that equation that we just came up with, the one for the total change in parcel temperature with time, and put that into our thermodynamic equation. So we expanded the Lagrangian derivative, and we're going to take that and put that into dt dt in our thermo equation. When we do that, it looks pretty messy. In other words, the left-hand side gets a lot bigger because now we have more terms, and the right-hand side we still have the vertical term, the vertical motion term, and also the diabatic heating and cooling term. So we're going to rearrange this a little bit and solve for the local change in temperature with time. And when we do that, we're going to combine the terms also a little bit. We see that we have two terms on the right-hand side that have the omega. We're going to combine those. And then we are going to give those terms in the parentheses a special name. We're going to call those P over R times sigma. And that sigma is something new. The P is pressure, the R is gas constant. You guys remember that. But the sigma we're going to call static stability. That's something completely different, or new actually. And static stability has to do with the stability of the atmosphere. So this is our new equation. We kind of rearranged our equation a little bit, but it says the local change in temperature with a parcel, local meaning at a given location, is equal to, of course, horizontal temperature advection, but two other terms. Also vertical motions, as the air rises through the atmosphere or descends, the temperature changes at a given location. And then also it depends upon how much diabatic heating, in other words, latent heat, radiation, conduction occurs at a given location. So that's the start of the thermodynamic equation. We're going to take this and try and derive vertical motions as a result of temperature advection. And we'll do that in the next video.